In this video, I am going to talk about Bernoulli differential equations. Bernoulli differential equations are of this format: dy over dx plus p of x times y is equal to q of x times y to the power n, with a special attention that n cannot be 0 or n cannot be 1. If n is 0, it's y to the power 0, which is 1. In that case, the equation becomes just a regular, normal, first order differential equation, linear first order differential equation. If y is equal to n is equal to 1, it is going to be y to the power 1 is equal to y. In that case also, this becomes a linear first order differential equation, and we can solve those. All right. So if n is not 0 nor n is equal to 1, in that case we have Bernoulli differential equation, and of course these equations are non-linear by nature. So to solve these differential equations, we kind of apply a special trick, and that trick is this. So my original equation is dy over dx plus p of x y is equal to q of x y to the power n. Now I'm going to divide both sides of this equation by y to the power n, y to the power n, and y to the power n. And that gives me 1 over y to the power n dy over dx plus p of x times y to the power 1 minus n. Y divided by y to the power n is y to the power 1 minus n is equal to q of x. And this cancel out. Now I will take this nonlinear differential equation and actually convert it into a linear differential equation that we can solve. And we do so by using substitution. And at this point, I would like to emphasize the fact that substitution is an extremely powerful tool in mathematics. Okay, there are problems that you cannot solve directly. However, when you do a substitution, the problem becomes manageable. You can solve it with existing tricks or existing things that we already know. In this case, here is one example, great example. So what I'm going to do, I'm going to say z is equal to y to the power 1 minus n. That means my derivative of z with respect to x is going to be equal to derivative of y to the power 1 minus n with respect to x. And that is going to give me dz over dx is equal to 1 minus n to the power times y to the power 1 minus n minus 1 times dy over dx using the chain rule. So dz over dx is going to be equal to 1 minus n times y to the power negative n, right? This 1 and negative 1 is going to cancel, times dy over dx. So if I simplify it further, I get 1 over 1 minus n times dz over dx is going to be equal to 1 over y to the power n dy over dx. So y to the power negative n is 1 over y to the power n, and I divide both sides by 1 minus n, and this is what I get. So this is very important for you to pay attention to. By the way, look, this is the same as this, right? 1 over y to the power n times dy over dx. So then it must be this. So I can replace it by 1 over 1 minus n times dz over dx plus p of x times, now this is my z, right? So then this is going to be just z is equal to q of x. Now please note, this is wonderful. Just by doing a quick substitution, I have converted this nonlinear differential equation into a linear differential equation. Now this is something we can solve. This is something we have dealt with before. We have multiple techniques for solving this type of linear differential equations. Now let me go ahead and do an example. My example is dy over dx minus y over x is equal to negative x square y square. So this is of course a Bernoulli differential equation. So to solve this, we are going to divide both sides by y square. So divided by y square, and then divided by y square, and divided by y square. If I did that, I'm going to get 1 over y square dy over dx minus 1 over x times 1 over y is equal to negative x square. Now I can do my substitution. Let's say z is equal to 1 over y, or y to the power negative 1. That's going to give me dz over dx to be negative 1 to the power y to the power negative 2, because negative 1 minus 1 is negative 2, times dy over dx using the chain rule. And if I were to simplify it further, this is what I would get. It's going to be equal to negative 1 over y square dy over dx. That gives me dz over dx negative is equal to 1 over y square dy over dx. Now look, this is going to help me do the substitution. This is the same as this, right? So we are going to rewrite the equation as negative dz over dx minus 1 over x times 1 over y is actually z times z is equal to negative x square. Since it's all negative, I could go ahead and just get rid of the negatives. So that's going to give me dz over dx plus 1 over x times z is equal to x square. Now this is a first order linear differential equation in z. Now we know how to solve this. We are going to use the integrating factor. So mu of x is going to be, e to the power integral coefficient of z. So integral 1 over x dx, which is, by the way, equal to e to the power ln of x, which is just x. So my mu of x is just x. So if I multiply both sides by mu of x, okay, I multiply both sides by mu of x, which is x. So that's going to give me x times x times x. That's going to give me on the left hand side is going to be d over dx. I'm assuming here that you know how to do integrating factor. So z times x is equal to x cube. Now I can integrate it with respect to x. So integral dx, integral dx. So that is going to give me nothing but zx on the left, okay, is equal to, on the right is going to be x to the power 4 over 4 plus some arbitrary constant c. Now if I divide both sides by x, I'm going to get z is equal to x cube over 4 plus c over x. However, there is no z. Z was a substituted value, so, but z is 1 over y. So that tells me, so let me come to the left here. 1 over y is z. So z must be equal to x cube over 4 plus c over x. Now if I simplify it, y is going to be my y of x, right? This is going to be equal to 1 over x cube over 4 plus c over x. Let's put it inside a square bracket so that you can see it clearly. So that is my solution to the differential equation or Bernoulli differential equation. So I have given you here the theory behind Bernoulli differential equation, as well as I have given you an example. I hope that this clarifies things, and I hope that you understood the topics that I discussed. Thank you very much, and best of luck.